We talked about pipeline partitioning earlier in this lecture. So when is it that we can't do pipelining? Where does our pipeline break? Okay, and let's think about this in the context of the relational operators that we've implemented so far. Sorting is a big pipeline breaker, right? In order to sort things, we have to consume the entire input before producing any output. So sort merge join, for example, can't start merging until it's finished sorting, and that breaks pipeline parallelism. With hash join, the hash build phase also breaks pipeline parallelism. Building those hash table has to be completed before we start probing them. So Grace hash join can't start probing until its hash tables are built. And so we might ask, could we build a join scheme? Could we invent a join scheme that is fully pipelining and has no pipeline breakers at all? And the answer is yes. It's called the symmetric or pipeline hash join, and I alluded to it earlier. It's a single phase algorithm. It's fully streaming, and it works like this. Each node in the network is going to allocate 2 hash tables, one for each table, one for each side of the join. When a tuple of R arrives, we're going to build it into the R hash table by its join key, and we're going to probe for matches in the S hash table, and if we see any matches, we'll send them to the result. Upon the arrival of an S tuple, we'll do the same thing symmetrically. We'll build it into the S hash table, probe R for matches, and send it to the result. So R and S, you can't really tell which is left and which is right. They're fully symmetric, hence the name of the algorithm. And this is guaranteed, it may surprise you, but this is guaranteed to produce the correct answer for the join. Why does it work? Well, think about it this way. Every output tuple is generated exactly once. It's generated at the time when its second part arrives. Now, which part arrives first is non-deterministic. It might depend on network delays and other things. But once the second half of the tuple arrives, it will find its first half in the opposite hash table and appear in the output exactly once. This is a fully streaming algorithm, so you can always pull another tuple from R and S, build, probe for outputs. And so it's really nice for systems that you want to be streaming, whether these are on streaming data that never ends, or whether these are systems where you just want to get early answers from long-running queries on disk. So symmetric or pipeline hash join is a really nice algorithm for when you care about the responsiveness of your system and you want to stream data. It also gives you excellent pipeline parallelism, although remember that our pipelines are probably only a few operators deep, and partition parallelism is often where the big wins are. Okay, now I'm not going to talk about the rest in detail, but there are extensions to these join algorithms. There's a parallel version of symmetric hash join, which is straightforward. It's really part of the original proposal. You just add that streaming partitioning HN phase up front, and you get parallel symmetric hash join. It's very similar to naive hash join, parallel naive hash join, but with 2 hash buckets. So parallelism for symmetric hash join is a straightforward extension. If you want your symmetric hash join to work out of core, that's quite a bit trickier. There's a paper called XJoin that describes how to do this. It's by Urhan et al. It's an interesting piece of work. It hasn't been implemented in a lot of systems to my knowledge. There's also, interestingly, a non-blocking sort merge variant called a progressive merge join, which also has no blocking. It doesn't quite sort things fully, and that's how it gets away with it. And again, that's an interesting research paper you might want to read if you're really interested in streaming algorithms that run out of core.